applause to Mr. Kevin Welch.
Yeah, actually, as Tom was saying, over 20 years, I just realized it's pretty close to 30 years now that I've been programming. I started out in COBOL and all kinds of early stuff, so I've been around a while. Ruby on Rails for about 7 years now, Objective-C for over 2 years, mostly writing private party business applications, so not so much the consumer-facing stuff. So I'm going to talk tonight about Objective-C and what it suggests about the future of programming. Now, I created maybe a few too many slides with a few too many details, so I'm going to be skipping over a lot of the little code examples and just trying to stay to the high level tonight. So I'm doing this on the fly, adjusting things. All right, so what is Objective-C? Well, most of those cool apps on your iPhones and iPads are written in Objective-C, as well as most Mac applications are also written in Objective-C. That's where most of the Objective-C is in the world. It's a fairly advanced language in certain ways, but it's also a paradox. See, Objective-C is an anachronism because it's based on an older language called C, hence the name Objective-C. So C was invented in 1972, so it's 40 years old, slightly younger than me. It's been widely used since then in a lot of systems programming. It's a very powerful language, but in some ways it's primitive compared to the more modern application languages. And so C is a compiled language. It's statically typed, and again, I was going to go into more detail about what that is, but I'll skip over that for now. Just know that it's a very it's statically typed and statically bound I mean, you can get around some of that, but that's what it's really considered to be. There are no object-oriented features in the language at all. Everything is written into functions, which are basically subroutines. So Objective-C is a strict superset of C. And what that means is you could write an Objective-C source file, and it can consist of nothing but C syntax and constructs, and it would compile just fine. And Objective-C just adds a layer on top of that. So Objective-C itself is over 30 years old. It was invented in the early 80s. So again, Objective-C is an object-oriented language. It introduces some dynamic typing and dynamic binding, which just means all of this stuff happens at runtime. That gives it a lot of flexibility compared to C. And you can write some very, very general plug-in libraries with it. And all this is enabled with an advanced runtime, which is compiled in with the applications. It's very powerful. There are some trade-offs. You lose some optimization and efficiency to get out all that flexibility. So this is one of the slides I just added. I want to talk a little bit about the popularity of Objective-C. This is actually the August 2013, I don't even know how you pronounce that, TIOBE. I mean, I've always just read it, but it's just gauging the popularity of languages based on search engines. So it may not be a perfect reflection of the actual popularity or utility of the language, but I don't know if you can even read it. It's the fourth line. It's the fourth most popular listed there. There's a little red arrow pointing down, but I think that's an artifact of the data and not of what's really happening with the language overall. So it's a very popular language. Actually, it's the only, you see that little black line at the bottom that ticks up in 2009? Oh, let me move out of the way if you want to see that. So it's actually, since 2009, it's right up to here. So it's had some success in the past few years for very good reasons. I mean, one obvious factor is the popularity of iPhones, iPads, but it also has some very advanced programming features, and I'll just give you a quick summary of those. Again, there's that dynamic typing, and again, this is a code example that I'm not going to go into in great detail now, but that's one of the features that makes it very powerful. Dynamic binding, method implementations are selected at runtime. This enables some very powerful programming techniques, something called duck typing, where unrelated components can be compiled at different times by different people, sent the same message. If they're, of course, a human and a duck might respond differently to quack, which is what you would expect, but you can have the same variable refer to objects of any type like that. As long as they can respond, they will. So it gives you a lot of functionality with less code, greater library reusability, the plug-in components that put these applications together. There are also some functional programming features of the language. I think Peter's going to talk a little bit about that tonight, if I'm not mistaken. So it's not a very complete or very strict implementation, but you can do it with something called blocks in Objective-C. So they're very, very expressive. And I wrote examples. Again, I don't want to go into the great details because it would really just take too long. And there's another advanced feature called metaprogramming. Now, metaprogramming is just code that examines or generates more code. And that comes in a couple of flavors. Reflection or introspection just means a program can look at itself, at its own structure. And method insertion just means it can actually make changes to itself while it's running. Again, you get a lot of functionality with less code, so you get some productivity out of that, and more of that reusability, convenience APIs. These techniques are actually very well known in the Ruby on Rails world, but you can do them in Objective-C as well. So programs that modify themselves, I think that's going to become more common as we go. Again, there are a lot of techniques in Objective-C for doing this. I don't know if I want to go into the great details about that. You can add whole categories of functions or methods to an existing class. And actually, this is an example where I actually did that. I took this standard array, which is like a collection in Objective-C, and added methods to it. So you're really modifying some pretty basic features of the language when you do that. There is a need for a great deal of concurrency in modern applications. That concurrency just means conceptually more than one thing happens at a time. Now, there's limits on the hardware we have, but a lot of our modern computers, they have multiple cores. They have so a lot of things can happen at one time, but it's really hard to get this right. So there's a lot of abstraction in the Objective-C standard library for making that easier, and making it easier so you don't have to step on yourself when you're doing it. So again, I'm probably not going to go into great detail. There's a couple of abstractions in the language for doing that. Another thing I think is becoming very common is this whole idea of interacting with our machines with natural language. And obviously Siri is a very popular example of that these days. Right now it's hard to program against Siri because I don't think Apple provides any APIs to do that. I think they will soon, I hope anyway. So, but there are plenty of third-party examples and alternatives, and I just think that's just going to become more common as we get better at it. She doesn't understand half the things I say right now, so I think it's still kind of early days for that. But we'll see it more often. All right, so distributed computing. What that means is your application functionality is distributed across devices and across servers, usually connected with networks. They may be connecting with servers in the cloud or what have you. This is very popular with social applications, your Facebook applications, your LinkedIn applications underneath its native application on these, but it still talks to the rest of the world on the back end. Other use cases include, interacting with Dropbox There's applications for all this stuff on there. This diagram is kind of the way my news search app works on these machines. So it has to talk to the internet and search the news because it doesn't have it locally. But it's a native application. So visual programming is kind of I want to call it a retro-futuristic idea. I mean, it's been around for a while. The idea has been, the idea is to arrange or connect graphical objects together to build up your program logic. Now, it's a neat idea. Computer scientists have been working on this for a long time, but it's really hard to make it work well with abstract programming logic. So I don't know when and if that's ever going to catch on. But for certain applications, like designing your application's user interface, the way it interacts with the users seems to work fairly well. And in the Objective-C world, Apple's interface builder is a great example of this. This is actually the flow and the structure of my own my news search app in Interface Builder. And I think the Apple's tools are kind of shining the way for the future of this approach. I think interaction with physical sensors is as targets of programming. I mean, that's just going up with time, and they interact with mobile devices. You have sensors built into your iPhone, your GPS, your accelerometer, your camera, and if there's something that is not in there, chances are there's a third party developing it now that you'll be able to attach to your phone. So, heart rate monitors, seismometers, medical imagers, all of that stuff there's plenty of room for growth in that field. So we're going to have a Star Trek tricorder before long, I think. All right, so Objective-C has some really advanced features for developing very advanced applications, and I think there's going to be tremendous growth in that world. But there's still a lot of room for even further advances, and that's what I'm going to talk about just for a little bit longer here. So in the longer term, I think that we're going to get even more mobile. And so our programming techniques and tools are really going to have to adapt. For one thing, I think our two-dimensional gestures that we use on these devices, your swipe, your pinch, and your rotate, on a flat surface are going to become three-dimensional in time. And so we're going to have to be dealing with, grab and move and rotate and be receiving feedback either in virtual worlds or in the real world, kind of overlaid with virtual objects. So you're manipulating virtual objects. All of this implies that we're going to have to do some very, very careful programming. I think there's so much work to do in that side. One of the things that I struggle with is sometimes accidentally making a gesture that I don't intend to make just because I hiccuped or something like that. You don't want to sneeze and accidentally execute an order to buy 10,000 shares of stock in an alpaca farm if that's not what you intended to do. So I think the harder thing is actually going to be the interface design. So I think we're going to move also from something we hold to something we wear, to something on us. Smartwatches are kind of all the talk these days, and I'm sure we're going to be seeing more of those. Google Glass is another great example where you wear your glasses and there's a little visual display in the corner that you can look at. But I think this is going to go way beyond that. It's going to go. Our clothing is going to become programmable. Our shoes, we're going to have, gloves, we're going to have bone conduction sound. I think all this stuff is coming. But even beyond that, I think we're going to be moving eventually from something on us to something in us. And one example that I think of is cornea implants. Eventually we're going to actually have the heads-up visual display kind of integrated with our eyeballs. I know that sounds strange, but I'm kind of looking forward to that. So I'm weird that way. But sooner or later we're going to have those heads-up displays kind of built into our eyes, and eventually I think it's going to move into direct brain stimulation with nano devices implanted. So in that day, our visual cortex will be stimulated. So we'll see what we need to see. We'll probably feel what we need to feel, and hearing kind of the whole thing. And we'll be giving commands by thinking them. So that's something called subvocalization. If I want you to imagine for a moment, think about the bridge on the Starship Enterprise. All right, but think about it like this. What if people were just sitting in a relatively empty room and just thinking to control a ship? That may not make for great cinema, but I think that by the time we're building starships, that's how we're going to be controlling them. This is all kind of far future stuff, but I think it's inevitable if we continue to develop the technology. And all of this implies, in terms of programming, that we're going to have to be more and more careful about thoroughly validating the correctness and the safety of our code. Because we don't want, low-quality software running hardware that's practically a part of us. I mean, it gets more and more dangerous. So that's kind of my take on it. We're developing some automated tools now, and they're becoming more and more used, but I think we're going to have to get better at that. So there's that. That's how I see it. And this is my contact information. You got questions?
Why isn't Objective-C C++?
Because it was developed by different people. There's really no other reason. The C++ is an object-oriented take on C. Objective-C is just a very different philosophy for doing it.
I thought you said it was object-oriented.
Oh, C++ is object-oriented, Objective-C is object-oriented, C is not. But they're just two different approaches to making C object-oriented.
But Objective-C is closer to C++ than to C, or you would disagree with that?
Closer? I don't, no, I wouldn't say that. It's just different. It's different. It's different.
I was going to say, is that based on the fact that Apple doesn't really share its, it wants exclusivity of everything that has to do with its products, including the program language?
I wouldn't say they're different because of that, because they were both invented roughly in the same era. And Apple didn't own Objective-C at the time. They do now. So that may be true going forward, but in the past, it's an artifact of history, the way I look at it, and of computer scientists having really different philosophies for how to do object-oriented design. Because, I mean, Objective-C was designed from the beginning to be very dynamic, to do all this late binding and runtime typing and all that. And C++ was not.
So any other questions? All right, let's give Kevin a big round of applause. All right, let's give Peter Jones a big round of applause here.
Hi, everyone. I want to talk in my very brief moment I have with you tonight about the current state of software development, where we are today, where we're going tomorrow, and where we need to be going tomorrow. I don't think I need to mention to anyone in this room that software is ubiquitous. I'd imagine that all of us here tonight have at least one, if not many, devices that have a general purpose CPU running software. It means we're all part of this big family of bugs, crashes, and software updates. When I think about this reality, it's almost somewhat funny, because I'm reminded of being a child and dreaming of the future of advanced technologies, things like flying cars. I never thought that I would be rebooting my television or refrigerator because of bugs. I think that we're in an era that's where we have an epidemic of quality problems in the software. And it's not new. People have been writing about this since the 70s, about how software is exploding. And like Kevin mentioned, everything's becoming software. But I'm sure that everyone in this room recently has probably crashed an application or an operating system, or at least made it act in ways that you didn't expect. Or maybe even you've seen that box on a web page that says, "We're sorry, an error has occurred. We know about this. Please try your request again later." And this is where we are today. And I think this epidemic is caused by two fundamental things. One is that there's this immense business pressure on software developers. So if you're a software developer, you've probably felt this pressure to produce very creative solutions to very complicated problems in the smallest amount of time as possible. And when a business is faced with the trade-off between time and quality, they almost always choose time. And so as software developers, we have to cut corners, and that mostly results in a reduction of quality. The other factor is slightly more subtle. And as software developers, we've allowed the idea that bugs are inherent in the process of software development to leak into popular culture and to believe that ourselves. I've been writing code for over 20 years, and until recently, I also believed that bugs just came along with the ride. It's part of software development. You can't separate them. We're humans. We're the ones writing the code. We make the errors. There's no way to write bug-free software. But I'm here to tell you tonight that's not true. The tools exist today, and there are tools being written right now for tomorrow that do allow us to get very close, if not right where we need to be, to write bug-free software that conforms to the specifications of the business application. I want to talk tonight about one of those tools, and that's Haskell. What is Haskell? Well, it's a programming language, simply, but more specifically, it's a general purpose language. Now, you've probably heard of other general purpose languages like C, C++, Java, Python, Ruby. Haskell can do all the same things that these languages can do because it's also a general purpose language. Now, I bring this up specifically because Haskell is very different than those other languages. So you may have not heard of Haskell, but if you have, you may have heard things like Haskell's very difficult to use, or even that you can't use Haskell to write real-world software to solve real-world problems. And of course, those are myths, but where do they come from? And it's because Haskell approaches software development from a completely different perspective than most languages. And so software developers, we hear about some of the things that Haskell promises us. We investigate the language, but we come to the language and we approach it like we do every other language you've ever approached. And we hit a brick wall because Haskell doesn't approach programming like other languages do. Let me talk about why. Most languages approach programming as an abstraction over the machine itself. As programmers, we write a sequence of instructions that get executed on the CPU in a specific order. Or, in other words, we are commanding the computer to perform tasks in a very specific order. And we do that because it seems very intuitive. But I say seems, because in reality, when you read the text of a program, you can't actually predict what's going to happen when that program's running. Unlike we'd like to believe in traditional programming that you can just read the text of a program and the program is going to execute from top to bottom and we can reason about it and decide whether or not there's going to be problems. But a program is much more complicated than that, right? There's branching. A program might go this way if this is true and this way if this is true. And it turns out to be a fallacy that that's going to execute sequentially top to bottom. Haskell, on the other hand, starts with an abstraction over mathematical expressions. We don't write this sequence of steps that are going to be executed in a specific order. Instead, we write computations that result in a value. And these expressions look very mathematical. A lot of the terminology in Haskell is very mathematical. And a lot of the solutions that Haskell programmers use are very mathematical. The truth of it is that software development has largely ignored mathematics for decades. But all the problems we face on a day-to-day basis as software developers have been solved 50 years ago by mathematicians. So Haskell prefers to leverage those solutions that mathematicians have come up with already and base solutions in those mathematical abstractions and solutions. But for an average programmer, it means a lot of foreign terms, and things look weird, and your initial reaction might be, oh, something's broken here, you can't really use this language. But I think it's actually worthwhile to learn those extra couple skills you need to write better software. Now, I really don't have much time tonight to compare this program to this program, or something written in Haskell to something not written in Haskell. But I do want to cherry pick one thing that I believe makes Haskell much different than other languages, and I would say better than other languages. In programming, we have this concept of a null pointer or a nil object. If you're not familiar with that, essentially it means an invalid value. Let me give you an example. Let's say there's some code out here that I want to use, and it will tell me somebody's middle name. I give them a name, and it'll give me back their middle name. Well, maybe you don't know, but not everybody has a middle name. So how does this code deal with the situation where someone doesn't have a middle name? Because it's promised to return a name. Well, in most languages, it will return something like return a null pointer or a nil object, this invalid value. And it's substitutable for a name, meaning that I can't tell the difference between them until the program's running. Now let me make this a little more interesting. Let's say I'm actually tasked with providing someone's middle initial. And I haven't had my coffee for the morning, I'm not on my A game. And in my worldview, everybody has a middle name. My entire family, everybody has a middle name. All my friends, they all have middle names. So I began by saying, oh, well, the easy thing is I have this code that gives me a middle name, and all I have to do is reach into that middle name and pull out the first letter. And we all know that if I reached into this, if I gave it to somebody who didn't have a middle name, it'd give me back this invalid object, and if I reached into it to get the first letter, I'd crash the program. But when I write all my tests, my ruled view says everybody has a middle name. So all my tests include people with middle names, and my tests all pass. As far as I'm concerned, I've covered all possible scenarios, as far as I can possibly predict. And I push this out, deploy it to my customers, they download it or whatever, and some poor soul who doesn't have a middle name runs my software and crashes the program. Now, is this sort of thing really a problem? I've had this debate with lots of software developers, and other developers have told me, well, any programmer worth their weight in salt would not do something like this. Any competent programmer would know better. But I think I've given you a pretty good example that's very simple, actually, to show you that you can't always anticipate every possible scenario. And based on our own experiences in life, it's what we're going to test on and what we're going to expect to come out of this. So to make this a little more interesting, I decided to go and try to discover how much of this is this really a problem or not. So I went to a website called GitHub. I don't know if you're familiar with GitHub. It's a website where software developers can upload their source code to share with other people. So if you're an open source software developer, you may upload your code to share with the world. If you're a commercial software developer, you may upload your code to share with your teammates. GitHub also has a bug tracker where people can create defect reports. And so I searched defect reports. I started by looking for any projects that had problems with null pointers and nil objects. And I started with the C programming language, actually, because in C, it's a very popular language, even though it's old by, well, it's older than I am, but it's old. And it passes around null pointers. Uses null pointers quite often. It's a very fundamental part of the language. So I search for any bug reports involving reaching into that invalid value and crashing the program. Or in C talk, it's called deferencing a null pointer. And I found a little more than 1,400 bugs on GitHub. Then I decided, well, other languages have the same issue, like Ruby. And Ruby doesn't have null pointers, but it does have something called nil objects. And they stand for this, basically the same thing. If you reach in and try to interact with a nil object, you'll crash the program. And in Ruby, we have just over 2,700 bug reports on GitHub. And I did the same thing for Python. Python has something called none, and JavaScript has something called null. Now, let me be clear. These numbers don't show us the prevalence of this problem, but they do show us that the problem exists. If you wanted to know more about how prevalent this problem is, you probably need to go and find out ratios, how often these problems are happening versus what percentage of problems are related to null pointers. But I think it clearly demonstrates that deferencing a null pointer or reaching into that invalid value does happen in real software by competent programmers. What about Haskell, though? Right? I'm up here talking about Haskell, so how does Haskell deal with this? Well, Haskell requires that every computation return a valid value. All right, so how do I deal with the situation? I already know that not everyone has a middle name. How do I deal with the potential for failure? Well, Haskell has a very powerful type system, and I can define my own type. And I can define that type so that it only can accept certain values. In this case, I would define a type that can only take one of two values. Either the name is there or it's not there. And in that one line of code, I'm essentially creating an annotation for the compiler, telling the compiler, hey, there are two situations here. Either there's going to be a name or there's not going to be a name. And I need you to keep me honest about that. And if I don't handle both situations, the compiler will not create the application for me. To be more clear, those bugs I was showing you in languages like C and Ruby and Python and JavaScript, those are happening at runtime. Runtime is when a user is actually interacting with your application. So a user is using your application and it crashes on them. That's runtime. On Haskell, or in a Haskell application, however, it's a compile time. That's when the developer is writing the code. So I've told Haskell there's two situations, and let's say I just ignore the situation where there might not be a middle name. The compiler will fail to generate the application and give me an error message saying, wait a minute, you did not handle this other situation. It is impossible for me to ship an application to my users that exhibits this type of problem. So Haskell handles this in two ways, really. One, it doesn't even have the concept of null pointers and nil objects. Haskell decides those are weak concepts we don't need. We already have a very strong type system, so we can have better abstractions. We can better support the idea of failure. We don't need that. And essentially, when you look back on C and other languages, that's really an escape hatch. That, oh, in all these situations, I'll return a middle name, but when I don't, here's my escape hatch. I do this instead. And Haskell doesn't have that escape hatch. Haskell says, no, you need to code the failure. You need to deal with it. Don't push it off onto your user. The second way Haskell deals with it is in the compiler, in the strong type system, by me saying there are two scenarios, and the compiler guaranteeing me that at compile time, both scenarios are handled. That I inspect the value and do the right thing in both situations. I just want to wrap up by saying that it's one use case, one small case where Haskell improves the quality of our software. It's not an end-all thing. And I would say that Haskell, I could sit here and probably talk 2 hours about how Haskell improves the quality of our software, all the things it gives us, all the tools it gives us to write bug-free software. And I'm with Kevin. If I'm going to replace my cornea, I don't want to do it in a language that can have these runtime failures. I want these things to be guaranteed at compile time before I put my eyeball in. Any questions? Absolutely. So the question is, how is Haskell different than other strongly typed languages like Pascal that promise to save us all? Haskell is a functional language, and it has a lot of other things like immutability, so variables can't change while the program's running. And it also forces us to compartmentalize side effects. So if you've ever written code, you know that any function can do one of three things. It can read its input, it can cause an effect by changing global variables or affecting the outside world, or it can return a result. In Haskell, you can only return a result. If you want to do side effects like affect the outside world, you have to do it in a special compartment under safety considerations. So beyond the type system, safety is a primary concern of the language. Yes?
Can you run a Haskell application on an iPhone?
You can. So Haskell is a high-level language, so the productivity is up there with like Ruby and Python. The question is, can you run Haskell on, say, an iPhone or an iPad? And so yes, it's a high-level language, but it's actually compiled like Objective-C is with an optimizing compiler. So it runs, it has the benefits, the developer benefits of being a high-level language, but it has the performance benefits almost close to C and C++. And as of right now, just recently, you can now compile for ARM architectures and write iPhone applications in ARM or Android applications in Haskell. Yes?
Haskell uses math, is what you said.
Yes, it's expression-based, so it's more like mathematical expressions versus sequencing.
Okay, and what I would say is regular programming languages don't use math traditionally.
Yeah, it's more, some of it looks arithmetic-like, but it's more about, the difference really is the purity. So in mathematics, a function is something that, given its inputs, will always return the same output. Like when you square a number, you always know what the result of that square is going to be. But in traditional programming, that's not the case. You call a function, it could return a different value every time.
And what I want to say is, from a traditional programmer's point of view, I'm really glad that I don't have to worry about math, because I suck at math, basically. And I can't even conceive of trying to do something, write a program where I've got to know partial differential equations or something like that.
No, that's more, when I say math is based on lambda calculus, not the idea that you have to know advanced mathematical topics, but mathematical abstractions. So if you understand set theory, and which is really easy when you think about it, it's only one jump up. Abstract algebra is not that much of a reach. You don't have to know advanced algebra or calculus. So I'm not talking about that type of math. I'm talking about solving problems and giving them names. So Haskell's popularity has been definitely growing over the last few years. Haskell is actually relatively old. I think it's about 25 years old. But only recently did they figure out how to allow side effects. So up until that point, Haskell's held on this idea of purity at all costs. And so the language itself couldn't do anything but make your computer warm, because it couldn't produce any effects that would change the outside world. And only in the last few years have they decided, now we have a great solution how to compartmentalize side effects. And because of that, it's definitely gaining in popularity. It's very popular in academics, of course, because it began as a research language. But now, because of its performance and because of its stability and safety, it's actually being used quite a bit in financial markets. Like there's a huge trading platform written in Haskell that can execute several thousand trades per second, and so forth and so on.
All right, let's give Peter a warm round of applause.
Thank you, everyone. Thank you.
Let's give Brian a warm welcome.
I appreciate the opportunity to come here and talk. This is definitely not necessarily the audience that I would generally be speaking to, but I do a fair bit about talking about data, in particular, not just because of I like to speculate and hack on my own, but because I think, and probably everybody here knows, like, data is going to become increasingly popular as we, as Kevin and Peter continue to develop their web apps or whatever they might be developing, iPhone apps, et cetera, everything is generating vast amounts of data. So I don't want to say that people like me are extremely important in this future world, but I do see a pretty good trajectory for my career path. So if I get out of the government. Anyway, I am a statistician at the National Renewable Energy Lab. I taught at CSU for a few years. Then I went to a startup in San Francisco because everybody was wanting to solve all the world's problems with these big data, or using big data as they call it. Turns out that what a lot of these companies want you to do is just count stuff, and I'm not that interested in counting stuff. And I wanted to move back to Colorado because I like Colorado more. I love San Francisco, but I think Colorado is better. So I looked for jobs and got a job at the National Renewable Energy Lab, which is cool. I deal with high performance computers. Part of my job is designing an API for how these big machines are going to interact with smart buildings in the future to do power aware scheduling and run power aware jobs. I'm also working on just how to utilize all the data that's coming off these high performance machines, and as well as buildings data, as well as weather data, as well as photovoltaic arrays, et cetera, combining all that data in order to design smart schedulers. Okay, so that's what I do now. But this is a talk on data. So I thought when I was asked to give this talk, I think I was in Iceland at the time, and I stupidly agreed, like, yeah, I'll have tons of time to make up a talk. Turns out I went on vacation last week, so I didn't have nearly as much time as I thought I would, and I had a paper due today, so I had a lot of stuff going on. But when I started thinking about this talk, I said, what would a typical data talk look like in 2013? One of the topics that you'll inevitably see is this big battle between data scientists, people who call themselves data scientists, or a statistician. I'm a traditional statistician, so I tend to come at it from the viewpoint as like, well, I'm a data scientist as well, because statistics is sort of the science of dealing with data, collecting, analyzing, et cetera. But just to give you an idea, there is a huge, I want to define data science in case you haven't looked at it. And one of the definitions that you'll often see is people will put up this Venn diagram and say it's this complicated thing that involves, computer hacking skills, math and statistics knowledge, substantive expertise. At the intersection of all those three things, you have data scientists. And I think that's sort of somebody that's coming at it from the non-statistical world in order to make themselves more marketable. So you have these, I don't want to dog computer scientists because I like computer science myself. But a lot of these people are saying, all right, well, I'm a hacker, or I have this substantive expertise. I'll know a little bit about math and statistics. I'll know a little bit about hacking, et cetera. And I'll call myself a data scientist because I can get a good job. But in any case, I feel like there's a lot of hype surrounding this term, and it's not really well defined, but this is what people tend to go with in their definition. Just to give you an example of a lot of hype surrounding data science, this data source handbook was written by Pete Warden. He's one of the guys. I wrote an R wrapper for one of his data science toolkits, but he's kind of famous in the data science community because he's not a trained statistician, but he's done a lot from the the non-traditional statistics point of view to enhance that data science term. In any case, I should also mention something about programming languages. As a statistician, my dominant language would definitely be R. If you've never heard of R, it's kind of a goofy language. It was designed by it was written by statisticians to do statistical work, so it's definitely not on the level of a C or C++. I can program in C or C++, but generally my work is statistics, so I do that. If I'm moving beyond that, nowadays I'll go into Python because when I worked at the startup, we were a Python shop and everything was in Python. On the big high performance computers, I tend to use R on that as well. In any case, let me get back to my talk because I'm not going to talk anymore about R. or another programming language. So a typical data talk, they might talk about infrastructure or how you're going to store your data. So you have these great debates about, do you want a SQL or no SQL or whatever? How are you going to analyze? Are you going to use Hadoop, MapReduce, that sort of thing to analyze your data? I don't want to get into that because people have done that online. You can read about all those debates. And for me, as long as I can access the data, whether it's in SQL, no SQL, whatever, I'm happy. So there are a lot of APIs that make the data accessible. Another thing that's very hot is surveillance. I don't want to talk about surveillance, but I think I certainly have a lot of opinions on the direction that surveillance is going. So after these talks, I'm happy to talk about that. Or they might just focus on big data. And what I mean by focusing on big data, they might say, all right, well, it doesn't matter, like, forget about traditional statistics and sampling theory, et cetera. All we need to do is collect all of the data. If we have everything, then statistics doesn't apply because we're dealing with n equal to all, and we're going to just we're going to make decisions based on that. A lot of the decisions that are based on that n equal to all paradigm are focused on correlations, which is completely fine in a lot of situations, but they don't focus on sort of the causation aspect of the problem. And that brings me to one of the quotes that was in Wired a few years ago. This Chris Anderson, he was the editor-in-chief at the time. He wrote this, I think it was called like The Age of the Petabyte, or the Petabyte Age, or something like this. And his quote was like, the data deluge makes the scientific method obsolete, because a lot of people had this n equal to all scenario, and they were just coming up, they didn't start with a hypothesis that they wanted to test. They were just coming up with, oh, these things are related, and let me explore that. And that's sort of that correlation versus causation mindset. But anyway, I think that's kind of a funny topic. I don't subscribe to that same theory. All right, instead, what I want to talk about, and this is maybe a longer introduction than I anticipated, but that's what happens when you sort of wait till the last minute to make up your talk and it doesn't flow as well as maybe you would expect. But two things in particular that I want to look at. One is datafication and digitization, and the other is data reuse. And it's not just a data reuse topic, it's more of data reuse, data combinations, how we're going to merge various things. And then the last thing, if I have time, is a little bit about anonymization. And that has to do a little bit with surveillance, although I'm not going to talk about the surveillance aspect. I'll just talk a few anecdotes about Netflix, AOL, et cetera. Okay, so how many people have seen this book? All right, well, good. This is a book by Victor Meyer Schoenberger, who's he's some sort of lecturer, professor or something at this University College London, somewhere in England. I can't remember exactly, but he does a lot with internet policy and privacy, et cetera. And he's kind of famous in that world. And then Kenneth Cukier, I'm not sure. He's the data editor at The Economist. So that Economist article that cover that I put up earlier, he had to be the one that was in charge of putting that whole thing together. And they've written an outstanding book. I can't recommend it enough. And it's called Big Data. So I call it the Big Data book. But what I'm going to do in this talk is I don't want to just simply do a book report on this particular book, although I find it, I think that would be like a terribly useful topic for another night. But I will kind of weave in some of the anecdotes that are given in this particular book with some of my own experiences in order to share what I think is sort of going on in the data world. So I'll talk about datafication and digitization first. If you never heard the terms, I feel like I should define them. Datafication is the process of arranging a phenomenon into a quantifiable format. Both of these topics are beaten, I don't want to say beaten to death, but they're definitely talked about in this particular book. And I took these definitions to some extent straight from the book, not straight from the book, but digitization means it's the process of turning some analog information into something that's binary, something that the computer is going to look at. And then I threw this quote up here just because I think it's pretty interesting. It comes from the book, and that big data is a continuation of humankind's ancient quest to measure, record, and analyze the world. And that's basically why I wanted to become a statistician as well. But let me back up a little bit and just talk about like an example story in this book about datafication and how it, a lot of people think of datafication as digitization, but it's definitely not. It's not a one-to-one correspondence here. Datafication, the story that I like to tell from this particular book, I didn't know about it. And of course, when I want to tell the story, I forget the name. But back in, I want to say the 1800s, the ships are going all over the world, and there was no good way to sort of map out the optimal route for going from Lisbon to somewhere else. They just kind of would look at the stars and follow these particular things. Somebody took it upon themselves to sort of trace out all these routes across the map and turn these logbooks that sailors had into a unified source of information. That was the process of datafying all these different logbooks, and then through that process he was able to come up with the optimal routes for various passages. So that's very different. I mean, that was back in the 1800s. We weren't talking about digitization then. We were just talking about how can we turn these sources of information into something that we can quantify and make decisions on. That was the process of the datafication, which is increasingly important. Digitization, of course, is important as well. Actually, I'll go ahead and start talking about data reuse because I have a few more anecdotes related to this. How many people have heard of Mike Flowers? Has anybody heard of Mike Flowers? Mike Flowers was an attorney working in the DA's office in New York City back in, I would say, the early 2000s. And this is a story that's been in the New York Times. I don't know him, by the way. This is a story that's been in the New York Times. It's in this book. In any case, he got bored with prosecuting people, so he said, all right, well, what can I do? I'm going to go to Iraq and try to figure out some stuff there, which, I mean, at the time, early 2000s, probably wasn't the best time to do this, but, he kind of wanted to throw a wrench into his everyday life. Went there, and he notices that when the Army or whoever was in charge of doing this, whoever was in charge of predicting where these IEDs were, was using all sorts of disparate sources of information in order to make predictions on where the IEDs would be. So they might have a collection of information based on just tales from the people talking in the town. They had their own sort of information, but they basically datafied all this different information, digitized it, and then were building predictive models on where the next IED explosion might be. And it was a very, despite the fact that you hear a lot about these explosions, it was very successful and it made a huge impact on him. So he got tired of that. He decides to go back to New York City, and he, convinces Michael Bloomberg that they should start making more data-based decisions, even though Bloomberg is a huge data advocate in the financial world, I guess. But he wanted to convince Bloomberg that the city should be taking data-based approaches to the problems that they're trying to solve. So somehow he convinces Bloomberg to give him a job as, I don't know if he was immediately determined to be the director of analytics of New York City, but he eventually became the director of analytics in the city. One of the problems that they first solved was the problem of, illegal conversions. So that's the process of taking a unit that's designed for 2 people, and turning it into something that might house 20. So they have extension cords running everywhere. They might have tons of rodents. There's a lot of issues that kind of go into this. And they have about, I want to say I don't believe I'm making this number up, but here that said, we suspect this house is a, illegally converted into a multi-person dwelling. Can you guys go inspect it? They have 200 inspectors go out and do this. They would, whenever they determined that something was a legitimate in their mind before they took this database approach, they would say, all right, well, we think that there might be, we think these are sort of the things that we really need to inspect. So they send their inspectors out. They had about a 13% chance of it actually being an illegal conversion. What Mike Flowers and his team did, in what's interesting about his team, he didn't go out and hire sort of the PhD level statisticians. He went out and hired people that were just smart and knew how to solve problems, which I think is an important part of this data world that we're living in. They built this model by pulling in information from the fire department, from people that were calling about like pests that are sort of on the streets, people that were, or data sets that were just freely available within the New York City data world, but they weren't being used together. So they determined, through their predictive model, they have a training set that they trained their data on, then tested it, and then employed it in the real world. Once they employed it in the real world, they increased the probability of an inspector going out to inspect a house. Rather than 13% chance that it was an illegal conversion, they bumped it up to about 70%. So I mean, that was just by combining all these pieces of information that originally had no business being together, and that's what I mean by this data reuse. Another story, this is actually from a friend of mine, the exploding manhole covers. Has anybody heard about this story? I think this is a great story. Okay. Well, so Cynthia Rudin, who's now at MIT, when she was at Columbia doing her PhD, she was, part of her PhD project was funded by Con Edison. And they had this problem. In Manhattan, all over New York City, there's this problem of, you could be walking down the street and all of a sudden a manhole cover explodes next to you. Hopefully that doesn't happen. But these manhole covers do explode often, or more often than you would like, because it sends this huge chunk of metal into the air at minimum, and then it's going to land somewhere. So what she did is she took all this data that had been collected. How much time okay. All right, she took all this data that she had been collecting or people had been collecting in New York City from the 1880s. I mean, they were just writing down, again, kind of like the person who did the shipping work, writing in logbooks, then it kind of developed, people were putting it in spreadsheets and doing other things, but then it was never actually brought into a single unified source where they actually inspected it. In her predictive model, the top 10% of manhole covers that she identified contained actually 44% of the next so many explosions. I can't remember what it was, but it was kind of a remarkable thing that they were that good at predicting these things. It turns out like the age of the manhole cover and whether they had a previous problem were sort of the dominant factors in that model, but nobody knew that beforehand. I mean, it seems obvious now, but until you actually go through that exercise and determine those factors, you don't actually know that. All right, well, I have tons of other anecdotes. I just want to mention with the icebergs and the Titanic, make sure you don't just look at the 10% of the iceberg. Look for, look for the other 90% of that iceberg, because there are often other uses for what you're collecting. All right, thanks. And questions?
Have any questions?
Yeah.
Are there any questions?
What sort of things do you do for NRA, for that National Renewable?
So I'm working on the API for, that interacts between, the high performance computers as well as the building in order to schedule smart jobs. And I'm also leading a project on, I'm a statistician. We have a very experimental high performance computer. If you're interested, I would highly recommend taking a tour because the machine's awesome. And it, not just because it can do a lot of computations, it's cool because it's run in a very different way than any other computer in the world or supercomputer in the world. So I thought, because it's so experimental, I thought maybe there would be a lot of reliability issues with it. In terms of component failures. Could be more, could be less, I don't know. But so I wrote a grant proposal to study the reliability of this machine. Turns out the people that fund these things don't want me to do that. They want me to do something else. So I'm working on another project, but it's directly related to the HPC.
Where is it NREL? Is that in Golden?
It's in Golden, but it's not what you would think of as Golden. It's sort of on the south side of South Table Mountain. So if you we're in downtown Golden and kind of went over South Table Mountain. It's kind of in the Denver West area.
Any more questions? I'd like to thank Ryan, Kevin, and Peter for helping us out tonight. I apologize, Tom is actually doing a video for DaVinci Coders, so I have to close this out tonight, and I do so well at that kind of stuff. Anyway, thank you very much for coming. Take a few minutes to get to know each other, and hopefully we'll see you next time. Thank you.